Hi everybody, I am Filippo Schiavio, a PhD student at Università della Svizzera Italiana. In this talk, I'm going to present the paper Language-Agnostic Integrated Queries in a Managed Polyglot Runtime. Modern data processing and analytics are often implemented in the language, which means that developers and data scientists, in particular during data wrangling and validation, use ad hoc solutions offered by libraries rather than relying on standalone systems like relational database. For example, because they often require complex setup and administration, and they suffer from inter-process communication overhead as well as serialization and deserialization overhead. In particular, data processing is often implemented in dynamic languages like Python and R. Data frames like pandas or dplyr are a common solution for data processing in dynamic languages. Unfortunately, data frames often show suboptimal performance. Moreover, they are designed for processing tabular data with typed columns, so not all the dynamic language features are supported. Embedded databases, such as SQLite, are an alternative solution to data frames. However, they often require a data ingestion phase, which means that collection cannot be queried in situ. There are some exceptions, for example DuckDB, which allow in situ query execution, but only on few selected typed data structures which are basically data frames. As a result, both data frames and embedded databases cannot query in situ all object collection, and some language features may not be available in the engine. Language-integrated query frameworks are a flexible solution which integrates the query engine in the language runtime. In this way, all the language features are available in the query engine. Moreover, Lean frameworks allow in situ query execution on any iterable, which means that the query can be executed directly on the object stored in the heap of the runtime without requiring any memory copy. However, state-of-the-art optimization of link systems are based off ahead-of-time compilation, and the compiler relies on the knowledge of the type system for generating specialized code. This is challenging in the context of dynamic languages, for which the type of a variable is known only at runtime. Indeed, even compiling a trivial query like the one in the example could be problematic, since the implementation of the less than operator depends on the runtime types of x and y. Our goal is implementing a query compiler not for a single dynamic language, but for more than one. This is motivated by the intuition that even if languages are different, they share a set of abstract operations. For example, reading the property of an object, accessing an array element, or calling a function. Indeed, a query engine for dynamically typed collection can be designed by abstracting the semantics of a specific language. In particular, the query engine implementation should focus on query operators and optimization, decoupling the implementation from the data access operation of a specific language. Existing query compilers, like statically typed languages, commonly rely on ahead-of-time compilation. However, dynamic languages do not, because at compilation time, the compiler cannot be aware of runtime types of variables. This means that the generated code should take into account all possible types. On the other hand, modern language runtimes employ just-in-time compilation, which is a completely different approach. In particular, program execution starts in interpreted mode, during which the virtual machine collects runtime information on the application. Then, program compilation takes place during interpretation, so at compilation time, the compiler has knowledge of observed types. We think that the just-in-time compiler of the virtual machines should be used to compile not just regular user code, but SQL queries as well. In the paper, we introduced DynQ, a novel language-agnostic query engine integrated in the GraalVM platform. Being integrated in the virtual machine, it can be simply imported as a library from any language executed on GraalVM. Technically, DynQ implements the backend of a SQL query compiler, which is built on top of the Truffle language implementation framework. In this way, DynQ is able to directly interact with the underlying compiler. As an example, DynQ internally exploits optimization like polymorphic inline caches and dynamic loop paralleling. The front end of the SQL compiler could be any SQL planner, Currently, we are using a partial site. Let's now have a look at an example of query execution on an array of objects with properties x and y of type integer. The example query is converted into a tree. Since DynQ is a push-based engine, the root of the tree is the table scan node, which pushes a row to the predicate node, which in turn pushes the row which passed the predicate into the count node. The last then node executes the comparison among the values obtained by reading the properties x and y. During interpretation, the query gets compiled into machine code, equivalent to the following pseudocode. The generated code reads the property x and y of the current object and it checks whether they have the expected type, which is the one observed during interpretation. In case the very same query would have been executed on an array of Python objects instead of JavaScript ones, the only difference from the point of view of DynQ are the implementation of the less than and read member nodes. All other nodes in the tree are exactly the same as in the previous example. Let's now consider the scenario where the same query is executed on objects with different types. In this example, we can assume that the first objects in the array are as in the previous example. Then other objects with x and y of type date. Also, let's assume that the query gets compiled when x and y have type integer. Once the first object with an expected type is encountered, the compiled code currently cannot deal with properties of type date. Indeed, it must de-optimize itself, meaning that the execution comes back in interpreted mode, and the interpreter can deal with any supported type through virtual call. Now DynQ is aware that dates are a possible runtime type, so if the query gets compiled a second time, the generated code will be able to deal with both possible types. Since DynQ is available in all the programming languages supported by the GraalVM platform, we can evaluate it on multiple programming languages and workloads. We use a TPCH as a macro benchmark and as a micro benchmark a set of simple queries on the TPCH dataset, which were presented in the context of Stream Fusion. On R, we evaluated DynQ on a dataset stored in R data frame against the DuckDB adapter for R and the data table package. In particular, we evaluated DuckDB in two different settings, namely query in situ the data frame, as done in DynQ, and preloading the data in DuckDB tables, which is more efficient. On JavaScript, we evaluate DynQ against Afterburner, which is an embedded database for JavaScript, and against Lodash, which is a popular data processing library. Our experiment measures the throughput of DynQ, evaluating the geometric means of query per second. We consider this experiment very important, since query engines based on compilation usually suffer from poor throughput due to the upfront cost of query compilation. DynQ, however, is based on dynamic compilation. In this way, the engine can start executing a query before compiling it, so the compilation is not an upfront performance penalty anymore. Indeed, as we can see by the graph, DynQ can offer both high throughput on small datasets with query interpretation and high performance on big datasets with query compilation. Regarding the JavaScript language, we evaluate DynQ against Afterburner. Since Afterburner does not allow in situ query execution, instead it requires data to be inserted in the database, we implemented DynQ adapter for the Afterburner memory layout. In this way, both engines execute queries on the same data representation. Our evaluation showed that DynQ is faster than Afterburner on both GraalVM and V8 in most of the queries, even on its own memory layout. In conclusion, with our work we presented DynQ, a novel query engine based on just-in-time compilation. DynQ is the first system which is able to execute queries in situ on object collections from multiple dynamic languages. Our evaluation shows that the flexibility of DynQ does not impair query execution performance. As a future work, we plan to expose DynQ as a standalone library which integrates the just-in-time compiler. In this way, DynQ could be integrated also in other existing data processing systems. That's all with my talk. Thank you very much for your attention. If you have any question, please contact me by email.